The objective of this lecture is to provide an introduction to kinematics using intrinsic coordinates. This lecture will be divided into the following parts. First, the theory of intrinsic coordinates will be provided. Second, a brief discussion of instances when intrinsic coordinates are useful. Will be provided. And finally, examples will be provided of using intrinsic coordinates. So first we're going to go through the theory, and then we're going to describe when this kinematic theory is useful, and then we're going to show you how it's actually used on some problems. So first, we are going to develop the theory of intrinsic coordinates. Now, to get started, before we get into the details, it's important to understand that intrinsic coordinates differ from other coordinate systems in that other coordinate systems are extrinsic. What that means is that they are external to the motion. So, in a typical extrinsic coordinate system, the coordinates are used to describe the motion, but they're not actually part of the motion themselves. They're not internal to the actual behavior of the object. The typical extrinsic coordinate systems are ones that we've already studied, which include Cartesian coordinates, cylindrical coordinates, and spherical coordinates. Now, intrinsic coordinates are internal to the motion. And as we're about to see, what that means is, depending upon the path that the object is taking, that's how the intrinsic coordinate systems are defined. So intrinsic coordinate systems, or intrinsic coordinates, are defined from the path taken by the object. Now, in this case, the object is a particle or a point. So as we'll see, when we get into intrinsic coordinates, we're going to actually be using the information about the motion of the object in order to be able to define these coordinates. So in order to get started, consider the motion of an object, in this case a particle or a point, relative to an arbitrary reference frame A. Now, the motion that we're going to see, or the motion that we're going to observe, will be relative to A. So the intrinsic coordinates are defined, or will be defined, relative to A. And here's what that picture looks like. So A is an arbitrary reference frame, and it will be depicted as follows. I have a reference frame A, and I have a point O that's fixed in A. And there's a point P whose motion I'm observing. So there's the position of P relative to O, and here's point P. Now, as this object moves, or as this point moves, it traces out a curve. So here's the curve that it traces out. And that curve is the path of the particle. So this is the trajectory, or the path of the particle relative to A. And at any point along the motion, the particle has a velocity. And that velocity is the velocity of this point as viewed by an observer relative to A. So Vp in A is the velocity of point P as viewed by an observer fixed in A. So Vp in A is the velocity of P as viewed by an observer fixed in reference frame A. Now, suppose we take that velocity and we divide it by its magnitude. So I'm going to define a vector. I'm going to define this vector to be E sub t. So E sub t is the unit vector along the velocity of P in A. So ET is equal to the velocity of P in A divided by the magnitude of the velocity of P in A. And this vector is what's called the tangent vector of the trajectory of P relative to reference frame A. Now we're going to add to this some other definitions that will help us describe this intrinsic coordinate system. But this vector ET is the first vector in this system, which I'm going to call intrinsic coordinates, or an intrinsic basis. Now, in order to be able to make this a little bit easier to understand, we're going to define what this magnitude of this velocity is now. So let VPA, which is like a script V, equal the magnitude of the velocity in A. This is what's called the speed of P relative to reference frame A. So if we use the speed, we can write the tangent vector is equal to the velocity of point P as viewed by an observer in A divided by the speed, where the speed is the magnitude. Now, once we have this vector, we know a couple of things. So we know that ET is a unit vector. So that implies that the magnitude of ET is equal to 1, which is an equivalent statement to the dot product of ET with itself is equal to 1. Now, given that the dot product of ET with itself is 1, we now know that this dot product, of course, is a scalar, but it's also equal to a constant, which implies that the rate of change of ET dotted with ET is 0, because ET dotted with ET is a constant. It's equal to 1. Now, because ET dotted with ET is a scalar, it can arbitrarily be differentiated in any reference frame. So because it can be arbitrarily differentiated in any reference frame, we're going to arbitrarily differentiate this vector in frame A. So therefore, d dt of ET dotted with ET can be arbitrarily set equal to d dt in A of ET dotted with ET, and that's equal to 0. Now, the reason I've differentiated in frame A is because A is the only reference frame I have. I'm watching motion relative to frame A. The tangent vector is being computed relative to frame A because it's the velocity of P in A divided by its magnitude, or in other words, the velocity divided by the speed, all in reference frame A. So the only frame in which I can take rates of change is frame A. So now let's take the rate of change in frame A. So what we wind up with is we wind up with d dt in A of ET dotted with ET is equal to, using the product rule for differentiation, it's det dt in A dotted with ET plus ET dotted with det dt in A. Now, because the dot product is commutative, so we know that A dotted with B is equal to B dotted with A, we can now write that this quantity that we have, which is the last quantity, is the same thing as saying 2 times det dt in A dotted with ET is equal to 0. So then we can drop the 2 to give that det dt in A dotted with ET is equal to 0. Now we see here that we have the scalar product between two vectors, and that scalar product is equal to 0. So if we assume that neither of these two vectors is the 0 vector, it means that these two vectors must be orthogonal to one another. So assuming that neither det dt in A nor ET is the 0 vector, it follows that det dt in A is orthogonal to ET. Now, we're going to define the direction of det dt in A because now we know it's orthogonal to ET. We're going to let En equal det dt in A divided by its magnitude. And this vector is going to be defined as the principal unit normal to the trajectory of P relative to reference frame A. So now this information can be put on a diagram to show with the directions of these different vectors where they lie, and to help visualize what's actually going on. So adding to the previous picture, here's my reference frame A. Again, here's a point O, and O is fixed in A. And then I have my point P, which is denoted as that point right there. And I have this trajectory of this point. So there's the trajectory of point P in reference frame A. And this vector that is tangent to this trajectory is ET, and along ET is the velocity of P in reference frame A. Then I have this vector that's normal to ET, which is the one I just defined. This direction is DET dt in A, and the unit vector along that direction is the vector I'm going to call E sub n, which is what I just defined. And then I define the vector EB, which is ET crossed with EN. So if I take ET and I cross it with EN, I get this vector right here, which is E sub B. And E sub B is equal to ET crossed with EN. And this is defined as the principal unit binormal to the trajectory of P in reference frame A. So now I've just defined a right-handed orthonormal basis, and that right-handed orthonormal basis is ET, EN, EB, and this is what's called an intrinsic basis. Now, you'll notice, as I said at the beginning of this lecture, an intrinsic basis is internal to the motion. So you can see that this basis is internal to the motion because I'm following this object or following this particle, and as I'm following it, there's a direction along which the particle is moving. That direction is along the velocity of the particle as viewed by an observer in reference frame A, because A is the frame in which I'm making my observations. And along that direction is what I call the tangent vector. The tangent vector lies along the direction of the velocity of P as viewed by an observer in reference frame A. From the definition of the tangent vector, which is along the velocity, I was able to construct this vector, which is the rate of change of the tangent vector in frame A. And that vector, from the math that I just did, must be orthogonal to the tangent vector itself. And I called the direction of DET dt in A, I called that EN. And then the cross product of ET with EN gave me the vector that I called EB, which is the principal unit binormal. So I've just defined it a basis, and that basis is an intrinsic basis, and it is internal to the motion. So it can be seen that the basis ET, EN, EB is internal to the motion. And that's why it's called an intrinsic basis. And unlike other coordinate systems, which are defined external to the motion, because this basis is defined internal to the motion, it has a very different structure from these other coordinate systems. Now, the important part of intrinsic coordinates, in order to understand the differences between this basis and other bases that come from other coordinate systems, is that in order to use intrinsic coordinates, it's necessary to start with some other basis and define intrinsic coordinates relative to that other basis. Now, this can be a little bit confusing at first, but let's write it down and then we'll work from there, which is that typically, well, not typically, but always, so it is the case that intrinsic coordinates are defined in terms of some other coordinate system. So it means that when we're actually solving a problem, we first have to set the problem up in another coordinate system, and then we compute intrinsic coordinates once we've set the problem up in that other coordinate system. So let's write that down too. So when solving a problem, first, a commonly used coordinate system is the starting point. And intrinsic coordinates are defined in terms of this other coordinate system. Now, it's often easier to work with examples to see how this actually plays out, but it's important to understand this concept first, that you don't start with intrinsic coordinates. So a problem is not started with intrinsic coordinates, but intrinsic coordinates are defined once another coordinate system has been constructed and is being used to set up the initial kinematics of the problem, and then we use intrinsic coordinates. Now, if you use this intrinsic basis, you can actually start by doing the following things, which make it actually fairly easy to be able to compute acceleration. And this is the advantage of intrinsic coordinates, is going back to an earlier calculation, we can recall that the tangent vector is equal to the velocity divided by the speed, which implies that the velocity of this point in frame A is equal to the speed in frame A times the tangent vector. So now let's differentiate this expression to get the acceleration. So then, the rate of change in frame A of the velocity of p in frame A is equal to the acceleration of p in frame A, which is now equal to the rate of change in frame A of the speed times the tangent vector. So now let's take the rate of change. So we get the acceleration of p in A is equal to, well, I have a product, so this is the rate of change of the speed times the tangent vector plus the speed times the rate of change in frame A of the tangent vector. Now notice that this first quantity, the rate of change of the speed, doesn't depend on the frame because the speed is a scalar, and so I can take its rate of change in any frame, which is why I don't have an A on that rate of change. It's just ddt of the speed. It's not ddt and A of the speed. But recall that now using this expression we have from earlier, that En is equal to det dt in A divided by its magnitude. So that implies that the rate of change of the tangent vector in A is equal to its magnitude times En. So I can substitute that expression up above to get the acceleration, which gives me the acceleration of p in A is equal to the rate of change of the speed in A times the tangent vector plus the speed in A times the magnitude of the rate of change of the tangent vector times the principal unit normal. And you can see that the acceleration, because I'm writing this in intrinsic coordinates relative to frame A, it doesn't have a binormal component. It only has a component in the ET and the EN directions. Now, it's useful at this point to understand that everything here is in terms of a reference frame or relative to a reference frame A. As long as I'm viewing motion relative to A, all of these quantities, ET, EN, and EB, and the speed and the velocity are all being computed relative to frame A, which is what allows me to get this expression for the acceleration in terms of all these quantities. Because if you look at this acceleration, you'll see that it depends upon the rate of change of the speed, which is relative to frame A. It depends upon the tangent vector, which is relative to frame A. And it depends upon the rate of change of the tangent vector, which again is relative to frame A. And it depends on the principal unit normal, which again is relative to frame A. So everything here is relative to frame A. And I know that I've said that now several times, but it's really important to understand that we're dealing with a single reference frame and we're observing motion relative to that frame. So now we have all the key results to be able to work our way forward to be able to solve some problems using intrinsic coordinates. So let's do a few examples and we'll see how this actually plays out. Now remember, when we start intrinsic coordinates, we always need another coordinate system first. So the first thing we're going to do is set up a kinematics problem the way we would normally set it up using the procedure that I developed in the previous lecture, and then we're going to compute intrinsic coordinates as we actually move our way through the calculations, and we'll see how this actually works out in a few problems. So here's the first example. So we have a point or a particle that's moving along what's called a logarithmic spiral. Now, a logarithmic spiral is a curve that has a particular shape to it. It looks like a spiral. It spirals inward, if you want to call it that. But it has this particular structure that if this is point O, which is kind of the center of the spiral, this point P, which is actually on the spiral itself, so it's like a track. This point P, the distance from O to P is R, and R is equal to R0 to times e to the minus b times the angle theta, where theta is the angle measured relative to this direction that I'm going to call horizontal. And I'm going to make this point, just for simplicity, I'm going to call this point Q. And OQ is kind of, it's like a horizontal direction if you want to think of it that way. And R0 and B are constants. Now, in order to set up this problem, we are going to start, like I said, the same way we would start any kinematics problem. So the first thing we're going to do is we want to compute. So this is the objective of this problem. The objective is compute or determine the velocity and acceleration of P as viewed by an observer fixed to the track. And this track is the spiral. So this is the track, which I'll denote T, which is also the spiral. So the first thing we're going to do to solve this problem is we need to determine the number of reference frames. So we know that there's one rotation. So one rotation implies 2 reference frames. Now those reference frames are the track itself, which is the base frame, and then the observation frame. Now the observation frame is the frame that is defined by the plane of out of the page and along OP. So I'm going to say A is going to equal the out of page OP plane, and this is the observation frame. And T, which is equal to the track, this is the base frame. Right, because the base frame is the frame in which we want all of our rates of change. But we're going to use intrinsic coordinates to do this problem. But we have to start with another coordinate system, so we're going to start with polar coordinates, and we're going to define these on the next page. So now here are my 2 frames. Remember, I'm going to go backwards from the last frame to the first frame. So A is equal to the out of page OP plane. And the coordinates that are going to be fixed to this frame are going to have its origin at O. I'm going to put ER along OP. I'm going to say EZ is out of page. And then E theta is equal to EZ crossed with ER. Now the next frame, which is the base frame, is T is equal to the track, and that's the base frame. Now the coordinates here are again going to have the origin at O, and then I'm going to define EX, EY, EZ to equal ER, E theta, EZ when theta equals 0. So here's what the picture looks like. Here's EX, here's EY, and here's EZ, and then here's ER, and here's E theta, and again EZ. This angle is theta. So when theta equals 0, these are lined up. Right now, I know that the position of point P relative to O is equal to RER. But R is equal to R0 times e to the minus b theta. So this is r0 e to the minus b theta er. So now the first thing I need to do is I need to compute the velocity. So until I get through computing velocity, I'm not actually going to get into intrinsic coordinates. It's really important that we start, again, you see we're starting this problem the exact same way we started other kinematics problems. So everything's the same up till this point. And it will continue to be so until we actually compute velocity, which is the next step. So I need the velocity as viewed by an observer fixed to the track, which I'll compute now. So then, the velocity of p as viewed by an observer fixed to the track is equal to the rate of change as viewed by an observer fixed to the track of the position of p relative to O. But the position of p relative to O is expressed in terms of coordinates fixed in the frame A. So I apply the transport theorem, and I get d dt in A of the position of p relative to O plus the angular velocity of A relative to t crossed with the position of p relative to O. Now, there are a few things that we can do fairly quickly, which is that d dt in A of the position of p relative to O is equal to d dt in A of r0 e to the minus b theta times er. But because er is fixed in frame A, I just have to differentiate this component or this coefficient in front. So this coefficient, when I differentiate it in front, gives me minus b r0 times theta dot times e to the minus b theta times er. So how did I get that? Well, the derivative of e to the minus b theta is minus b e to the minus b theta, but I'm differentiating with respect to time, so I have to multiply by d theta dt, which is how I got that expression. The next thing is, we know that the angular velocity of A and t is equal to theta dot ez, which implies that omega at crossed with the position of p relative to O is equal to theta dot ez crossed with r0 e to the minus b theta times er. So that implies that omega at crossed with the position of p relative to O is equal to r0 theta dot e to the minus b theta, and then ez crossed with er is e theta, which then gives that the velocity of point P as viewed by an observer fixed to the track is equal to the sum of these two terms, which gives me minus b r0 theta dot e to the minus b theta er plus r0 theta dot e to the minus b theta e theta. Now you can see that in this expression, r0 times theta dot e to the minus b theta factors out of both of these terms. So I get r0 theta dot e to the minus b theta times minus b er plus e theta. So that actually helps a lot, because now I can compute the speed and I can get the tangent vector. So recall that the tangent vector is equal to the velocity of p divided by its magnitude, which is also equal to the velocity of p, this time relative to the track, divided by the speed relative to the track. So now what I can do is I can compute the speed. So the speed is going to be the magnitude of this velocity. So let's actually go ahead and compute the speed. So we have that the speed relative to the track is equal to the velocity of p in magnitude, right? Which is equal to r0 theta dot e to the minus b theta times the square root of b squared plus 1. Now, how did I get that? Well, we have that any vector, if I take k times a vector b and I take its magnitude, that's equal to the absolute value of k times the magnitude of b. So in this case, what we have is we have that the magnitude of vp in t is equal to the magnitude of r0 theta dot e to the minus b theta times minus b er plus e theta, which is equal to the absolute value of r0 theta dot e to the minus b theta times the magnitude of minus ber plus e theta. Now, if we assume theta dot is greater than 0, which means the particle is moving forward on the spiral, so that's forward motion, on the track, then that implies that the absolute value of r0 theta dot e to the minus b theta is just equal to r0 theta dot e to the minus b theta. And also, the magnitude of minus ber plus e theta is just equal to the square root of the sum of the squares of the components. So that's equal to the square root of b squared plus 1, which is how I got the result that you see up above. So now what I can do is I can take this speed and take the velocity, and I can divide the velocity by the speed to compute the tangent vector. So then the tangent vector is equal to r0 theta dot e to the minus b theta times minus ber plus e theta, all divided by r0 theta dot e to the minus b theta times the square root of b squared plus 1. And you can see that the r0 theta dot e to the minus b theta just cancels out, and we're left with minus ber plus e theta, all divided by the square root of b squared plus 1. Now, this is where intrinsic coordinates starts. We now have the tangent vector and we have the speed. And once we have that, we can now write the velocity in terms of the tangent vector. So then, the velocity of point P as viewed by an observer fixed to the track is equal to the speed relative to the track times the tangent vector. Now what we're going to do is we're going to compute the acceleration in terms of intrinsic coordinates, because we can see here that we have the velocity in terms of intrinsic coordinates now, because we know the speed, right? So what we can do is we can use this expression and we can differentiate it to get the acceleration. So we know that the acceleration of p as viewed by an observer fixed to the track is equal to the rate of change as viewed by an observer fixed to the track of the speed relative to the track times the tangent vector, which is equal to the rate of change of the speed times the tangent vector plus the speed times the rate of change as viewed by an observer fixed to the track of the tangent vector. So that means we need to compute the rate of change of this tangent vector as viewed by an observer fixed to the track, which we'll do next. So now, the rate of change of the tangent vector is viewed by an observer fixed to the track. The tangent vector is expressed in coordinates fixed in frame A. So I have to apply the transport theorem. This is equal to dEt dt in A plus omega at crossed with et. Now, because the tangent vector et is equal to minus ber plus e theta, all divided by the square root of b squared plus 1, recall that b is constant. And because er and e theta are fixed in frame A, we obtain that the rate of change of the tangent vector as viewed by an observer in frame A is 0. So the only thing that's left is just the second term, which is that det dt in t is equal to omega at crossed with et, which is equal to theta dot ez crossed with minus ber plus e theta, all divided by the square root of b squared plus 1, which gives that det dt in t is equal to, well, we can go through the calculations. We have a theta dot that sits out front, and then what we wind up having is ez crossed with er and ez crossed with e theta. So ez crossed with er is e theta, and ez crossed with e theta is minus er. So we get minus er, and then we get minus b e theta once I flip these and put them in the right order. And I get the square root of b squared plus 1. So ez crossed with er again is e theta, but there's a negative sign already there, and there's a b. Ez crossed with e theta gives me minus er. Now, if you notice something about this, you'll also see that this can be written as minus theta dot times er plus b e theta, all divided by the square root of b squared plus 1. Now, we need to compute the normal vector, the principal unit normal. So we're going to take this expression and we're going to use it to compute the principal unit normal. So now det dt in t is equal to minus theta dot times er plus b e theta, all divided by the square root of b squared plus 1. So that implies that the magnitude of det dt in t is equal to the absolute value of minus theta dot times the magnitude of what's left over, times the magnitude of er plus b e theta, all divided by the square root of b squared plus 1. But the vector that's in the brackets, that's a unit vector, because the numerator, its magnitude is square root of b squared plus 1, and I'm dividing by square root of b squared plus 1. So that whole thing is just has unit magnitude, and the absolute value of minus theta dot is just equal to theta dot, because remember we said theta dot was equal to 0. So that implies that the principal unit normal, which is equal to the rate of change of the tangent vector in t divided by its magnitude, is just equal to det dt in t divided by theta dot, which implies that the rate of change of the tangent vector in t is equal to theta dot times en. So now we have all the information we need to be able to compute the acceleration. So we can use this expression and substitute it in to get the acceleration. So therefore, the acceleration of p as viewed by an observer fixed to the track is the rate of change of the speed times the tangent vector plus the speed times the rate of change of the tangent vector in t, which is equal to the rate of change of the speed times the tangent vector plus the speed times theta dot times en. So this last expression, in it we have the speed. So recall that the speed was equal to r0 theta dot e to the minus b theta times the square root of b squared plus 1. So that's the speed that would actually go in here. And we could differentiate this speed if you wanted to, just to get a complete description of what this thing looks like. But it's not really all that necessary, but I'll do it. R0 and the square root of b squared plus 1 are constants, so the only thing I have to do is differentiate the middle part. So I've got r0 times the square root of b squared plus 1 times theta double dot e to the minus b theta, and then minus b theta dot squared e to the minus b theta. Again, I'm differentiating with respect to time, and that's equal to r0 times, and I can factor out the e to the minus b theta. So I got r0 e to the minus b theta times the square root of b squared plus 1 times theta double dot minus b theta dot squared. So this last expression would go into the first term, and then the expression for the speed would go into the second term. So if I write this whole thing out, I would wind up with the acceleration of p as viewed by an observer fixed to the track is equal to r0 e to the minus b theta times the square root of b squared plus 1 times theta double dot minus b theta dot squared e sub t, and then I've got plus. Now if I substitute in, I've got r0, then there's a theta dot times a theta dot, which gives theta dot squared e to the minus b theta times the square root of b squared plus 1 times e sub n. That's the full expression for the acceleration. And of course I can still factor things out of this if I wanted to, but I'll just leave it that way so you can see what everything looks like in terms of et and en. So you can see when we're done here, we actually have the acceleration in terms of intrinsic coordinates, just like we had the velocity expressed in terms of intrinsic coordinates. But the key is that we started with a different coordinate system first, and then we converted to intrinsic coordinates after we got the velocity. So we're going to do one more example now, just to be able to finish this process to see how it plays out on a different problem. Now this problem, we actually used polar coordinates as the starting point. In the next problem, we're actually going to use Cartesian coordinates to see how these vectors are computed. So here's the next example. So suppose I have a particle moving on another track, and this curve is going to be described as follows. It's a bit of a complicated function, but we'll see what it looks like. Is that this here is y is equal to minus natural log of the cosine of x. So there's a point here P, there's a point here O, and this distance here horizontally is x. This distance is y, and y is equal to minus natural log of cosine of x. Now I'm going to define a point at the base here. I'm going to call that point Q. And because it's fairly straightforward to do this problem with one coordinate system, I'm just going to immediately define this basis. I'm going to call this EX, and I'm going to call this EY, and then EZ is going to be out of the page. I don't actually need another coordinate system in this case because there are no rotations in this problem. So again, the objective is determine the velocity and acceleration of P as viewed by an observer fixed to track. And again, here's the track. This is what I'm going to call the track, which is going to be denoted T. Now, in order to be able to solve this problem, you notice that there are no rotations. So there's 0 rotations, which implies we need one reference frame. Now, that one reference frame is simply going to be the track, and these coordinates EX, EY, EZ together with this point O, they are fixed in the track. So everything is already given in terms of the track, so we're done, because we know that this coordinate system O together with EX, EY, EZ, this is fixed to the track. I mean, another way of looking at it is that the track doesn't move relative to these coordinates don't move relative to the track, so either way it's the same thing. So we actually don't even need to define any frames and coordinate systems because they've already been defined, and we can just go straight into working with the position and then differentiate to get the velocity and move on forward from there. So then we know that the position of P relative to O is equal to XEX plus YEY, which is equal to XEX minus the natural log of cosine of x, EY. Now, because these coordinates are already fixed in the track, I know that the velocity of point P as viewed by an observer fixed to the track is just equal to d dt and t of the position of P relative to O, which is just equal to x dot EX plus y dot EY. And that is equal to x dot EX, and now I've got to take the derivative of y. So I've got 1 over the natural log, its derivative is 1 over the cosine, because it's natural log of cosine x, times the derivative of cosine x, which is minus the sine of x, times the derivative of x with respect to t, which is x dot times EY. So this gives x dot EX, and then you get plus x dot times the tangent of x, EY. So there's the velocity as viewed by an observer fixed to the track. Now this can be written, this last expression can be written as x dot EX plus tangent of x, EY. And now I actually have a way of being able to compute the speed fairly quickly, because I know the tangent vector is equal to the velocity divided by its magnitude, which is equal to the velocity divided by the speed, and I can compute the speed. The speed relative to the track is equal to the magnitude of the velocity, which is equal to the absolute value of x dot times the square root of 1 plus tangent squared x. Now, if you assume that x dot is greater than 0, then we wind up with the following expression. So assuming that x dot is greater than 0, and again that means we're moving forward, we wind up with the speed is equal to x dot times the square root of 1 plus tangent squared x. But from the trigonometric identities, we have that 1 plus tangent squared x is equal to secant squared x. So that implies that the speed relative to the track is equal to x dot times the secant of x, from which we can actually now compute the tangent vector. So we then have the tangent vector, which is equal to the velocity relative to the track divided by the speed, is equal to x dot times EX plus tangent of x, EY, all divided by x dot times secant of x. And again, you can see that the x dot cancels out, and we wind up with EX divided by secant of x plus tangent of x, EY, or I could write it this way, tangent of x divided by secant of x, EY. Now, secant of x is equal to 1 over the cosine of x. So that means I can multiply the whole thing through by cosine of x in numerator and denominator, and I get that the tangent vector is equal to the cosine of x plus cosine of x, ex, plus, now I've got cosine times tangent, but tangent is sine over cosine, so the cosines cancel out, and we wind up with sine of x, ey. So there's the tangent vector. We wind up with cosine x ex plus sine x ey. So now we know the speed, we know the tangent vector, and so now we can write the velocity in terms of the speed and the tangent vector as follows. We then obtain that the velocity of p as viewed by an observer fixed to the track is equal to the speed relative to the track times the tangent vector, which is equal to x dot secant x times the tangent vector. Where the tangent vector, as we recall, is equal to cosine x ex plus sine of x ey. Now, if we want the acceleration of p as viewed by an observer fixed to the track is equal to the rate of change of the speed times the tangent vector plus the speed relative to the track times the rate of change of the tangent vector. And again, we want to get all this in terms of intrinsic coordinates. So the rate of change of the tangent vector is viewed by an observer fixed to the track, because ex and ey are fixed to the track, is equal to minus x dot sine of x ex plus x dot cosine of x ey, which implies that the magnitude of the rate of change of the tangent vector is just equal to the absolute value of x dot times what's left over. Now, you can see that because you can factor out the x dot and you're left with minus sine x ex plus cosine x ey, but sine squared plus cosine squared is 1. So this is just equal to the absolute value of x dot, which, because we said x dot was greater than 0, it's just equal to x dot. So now we have that en is equal to the rate of change of the tangent vector in t divided by its magnitude, which is equal to the rate of change of the tangent vector divided by x dot. So we wind up with the rate of change of the tangent vector is just equal to x dot times en. So then the rate of change of the tangent vector is just in the track is just equal to x dot times en. So we can use this expression to compute the acceleration. So we then have that the acceleration as viewed by an observer fixed to the track is equal to the rate of change of the speed times the tangent vector plus the speed relative to the track times the rate of change of the tangent vector, which is just equal to x dot times en. So now what we can do is we can actually use the speed that we computed earlier. So we can recall that the speed is equal to x dot secant x, which means that, which implies that the rate of change of the speed is just equal to x double dot secant x and then plus x dot, and then we've got the rate of change of secant x, which is x dot squared times secant x tangent x. And that is what goes into this first expression. So we wind up with the acceleration of point P as viewed by an observer fixed to the track is equal to x double dot secant x plus x dot squared secant x times the tangent of x, the whole thing times the tangent vector, plus we've got x dot secant x times another x dot, because there's a second x dot that's multiplying en, so we wind up with x dot squared secant x times en. And that's the expression for the acceleration in terms of the intrinsic basis. So again, we've written this purely in terms of the intrinsic basis. And of course, we can factor out the secant x if we want to, and we're just left with secant x times x double dot plus x dot squared tangent x, but we'll just leave it this way because it's just as easy to leave it without simplifying it, just so you can see what all the steps are. So that's our second example. So now we've done two examples of using intrinsic coordinates. The first example used Cartesian coordinates as the starting point. Cylindrical coordinates as the starting point. The second one used Cartesian coordinates as the starting point. And in both cases, once we got to the point where we computed the velocity relative to the frame we were interested in, from that point forth, we defined the intrinsic coordinates, and we computed the velocity in terms of the tangent vector, and then we computed the acceleration and expressed it in terms of the tangent vector and the principal unit normal. So that takes us to the end of this lecture. So let's summarize what we've learned or what we've studied in this lecture. So first, we provided the theory of intrinsic coordinates. And then from the theory, we actually developed some concepts as to how to use intrinsic coordinates. And in particular, what we discussed was that intrinsic coordinates are used by starting with another coordinate system, intrinsic coordinates are defined in terms of this other system. And then finally, using these constructs, we studied examples of intrinsic coordinates. And that provides the foundation for how intrinsic coordinates are used. And again, typically they're used in such a way that you want to know something about what's happening internal to the motion. And that's the key to intrinsic coordinates, is that they describe motion internal to the motion as opposed to external to the motion, which is what extrinsic coordinates do. So that takes us to the end of this particular lecture, and we will continue on with the next topics in the lectures that follow.